Hello, I'm Maya Gupta. I'm a machine learning researcher here at Google, and I'm excited today to talk about the second key ingredient to making machine learning work great. You guys have already talked about minimizing training loss, that is, getting the examples right. And what we're going to talk about today is regularization, which, to sum it up, is not trusting your examples too much. As we can see in this curve called overfitting, as we go through more and more training iterations, our training loss is getting down. It's getting further and further down, and it keeps decreasing because that's what we're doing. We're minimizing the training loss. So no surprise that the blue curve keeps going down. Eventually, it'll sort of converge there. But the red line actually starts to go up. And the red line is what we really care about. We want to generalize. Even though we're training on the training examples, we want to generalize to new examples, the test examples, and we want to have low loss on them. So how do we keep the red line from going up, and what's going on here? Well, first of all, what's going on is overfitting. We're doing such a good job on the blue examples that we're starting to sort of fit to the unique perturbations and specializations of the blue examples. As an analogy, say you were trying to learn English, and the only person that there was to teach you English was a teenager. At first, that would really help you learn English, and you do a great job learning English. But if all you did was listen and talk to that one teenager, pretty soon you'd start to learn that teenager's slang and the particularities of their language and accent. And at some point, it'd make it even harder for you to speak English with the general population. So what can we do about overfitting? Well, regularization is what we do to avoid overfitting. And there are a lot of different regularization strategies. One is just to do early stopping, which says just stop the training before you've really converged on the training data, trying to get to where the bottom of the red curve is. But this can be a little difficult to do in practice, but often used. Other regularization strategies include trying to penalize the model complexity, and that's what we'll be talking about the rest of this section. And what we can do is we can penalize the model complexity while we're training. So far, the training has just focused on the important thing of getting the training examples right, minimizing the empirical risk minimization. Now what we're going to do is we're going to add a second term to penalize the model complexity. This is sometimes referred to as structural risk minimization. And so we're going to balance these two key ingredients, getting the training data right, but not trusting the training data too much that it makes our model too complicated. So how do we define model complexity? Well, there are a lot of things we could do. One popular strategy is to try to prefer smaller weights. That is, make the parameters as small as we can get away with while still getting the training examples right. And we could encode that mathematically in a few different ways. Today we're going to focus on L2 regularization, also known as ridge regularization. In this regularization strategy, we penalize the sum of the squared values of the weights. And if you're familiar with Bayesian priors, this sort of says that a priori, before we've seen our training examples, we would have guessed that our weights should be sort of centered around 0 and not too big, normally distributed. So when we use L2 regularization, it does pay attention to the training data, but it tries to make sure that we don't end up with any weights that are sort of bigger than they need to be. So let's put that together mathematically again. So now our training optimization has two terms. The first term, our training loss. We want to get the examples right. And you'll see that L term, the loss term, depends on the training data. But now we've added the second term for model complexity, and here we're using the L2 regularization, which is the sum of the squared weights. And you'll notice that that second term doesn't depend on the data. It just says, hey, I want a simple model. And you'll see these two terms are balanced by a lambda. That's a coefficient that says, how much do we care about getting the examples right versus making the model simple? And the choice of lambda is really up to you and depends on your problem. If you have lots and lots of training data, and your training data and your test data look the same, IID to be statistical, then you probably don't need much regularization, maybe 1 e to the -6, maybe none at all. But if you don't have much training data, or if your training data and test data are kind of different, then you may want a lot of regularization. And you may want to tune that with cross-validation or with a separate test set.